Hi everyone, this is my CS51 Problem Set number 8. And so we're gonna go through sections in order to understand each implementation. So the first one is just looking at the original case without all the added classes and looking at how it compares to the specifications for the neighbor radius being 4 and the infectiousness being 0.2. And so here I showed the simulation in a recorded video to see what it would look like based on the original case. And then I changed each variable. So I started with neighbor radius and I started with it letting it equal to 1. And then I made it 5 and then 10 and then 50. And so as you can tell, we have the not filled red circle, which clearly is increasing as we're checking this. So it's also showing us that the circles are being drawn correctly. And then I did the infectiousness, so it starts with 0, and this increases to 0.5, and then 0.75, and then finally 1. And so we see the difference in the graph as we increase the infectiousness as well. Next, I implemented quarantine. And so how quarantine would work is the infected person would have a chance of being put into isolation. And so I set the isolation to be the center of the graph. And then in order to better see it, I changed the color to green so that we could see it better on the graph, but also there is a counter so that we could see how many people are in quarantine at that time. And so the two factors that really change quarantine would be time and the chance that the infected person could be put into isolation. And so my original case is that it takes 5 for the time for the person to leave quarantine and go back to their original position. And there's a 1% chance that the infected person gets put in isolation. And so that would be found in this simulation. Then I looked at the two cases where we changed time and then we also changed the chance. So we set the time equal to 0, the time equal to 25, 50, and then the extreme case where the time equals 500. And then I changed the chance that the person could go into isolation from 1% to 5% to 10%. And then I checked another case such that the time equals 500 and the quarantine chance equals 10%, just because as we increase the quarantine chance, we already saw that the graphs are the same across 5% and 10%. So that was just an extra case just to see how it would change. And then next we have the grocery market implementation. And so in both the infected and the susceptible class, the people have a random chance of being put at this hotspot on the graph. And then once they're done with the grocery market, they're sent back to a random location. And so the original case is that they spend a time equal to 100 at the hotspot and that their chance of being sent there is 5%. And so that's found in this simulation. Then similar to quarantine, I changed the two variables. So we start with time equals 0, time equals 50, time equals 100, and time equals 500 to see how this would change. And then I started with the chance equal to 1%, 5%, 10%, and then 50%. And then finally we see 100%, which gives us a result that is strikingly 1,000 out of the 1,000 people are infected. So the last added implementation that I came up with was a ghost sort of class. And so this is meant for people who were deceased, but they have the optionality to become a ghost based on a chance. And when they're a ghost, they have the properties of being able to move around. And after a certain period of time, they can be revived. And so my original case for the ghost was that the time equals 100 and their chance of being a ghost is 2%. And so these are represented by the purple cross symbols that are floating around the graph. We note that these are purple just so that it's easier to tell between the gray cross that was the deceased. And then I changed the time that a person would have to be a ghost in order to be revived from 0 to 100 to 500. And then for the chance of being a ghost, it starts with 10 and then it goes to 50 and then to 100. And then I just checked another case such that the time equals 0 and the chance equals 100. And so that pretty much summarizes the implementations that I added. And so what I wanted to do next is put it all in a table just so I could see which ones stood out. And in gray, we have the highlighted maximums in each respective column. So the maximum number of deceased people were found when I used the ghost case such that the time equals 0 and the chance equals 100%. The maximum number of infected people occurred in the grocery store when the chance of being sent to the store would be 100%. And then in terms of susceptible, this happens both in the original case where infections is equal to 0, but also in quarantine when the chance of being quarantined kept on increasing. And then the highest group of recovered people occurred in the original case such that the infected radius or the neighbor radius is 10. And then the highest number of quarantine people would be when the people had to spend the longest period of time in quarantine. So that was T equals 500. And the highest number of ghosts would be when there was a 100% chance of being a ghost. And so overall, that concludes my summary of my implementations. So thanks for watching.